Today, as we continue our study of sets, let's talk about complements, subsets, and Venn diagrams. I want to begin by talking about something called the universal set and its complement. The set of all elements that are being considered is called the universal set. We'll use the letter capital U to denote the universal set. For example, if we were doing a survey on the month in which a person was born, then the universal set would be the set containing all 12 months: January, February, March, April, May, June, July, August, September, October, November, December. There are no more months to consider. That would be our universal set from which a particular month would be chosen for a particular person. The complement of a set A, denoted by A with an accent symbol as a superscript, is the set of all elements of the universal set U that are not elements of A. So you can't define the complement of a set until you know what the universal set is. For example, if the set J is the set containing January, June, and July, then the complement of J would be you go up to the universal set and you cross out the elements of J, which would be January, June, and July. That happen to be the months that start with the letter J. And what you're left with is the complement of J. So the set containing J complement is the set containing February, March, April, May, August, September, October, November, December. Let's try this example. Suppose the universal set that we're interested in is the set containing the counting numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. The set S is the set containing the elements 2, 4, 6, and 7. And the set T is written in set builder notation. It's a set of all x such that x is less than 10 and x is an element of the odd counting numbers. Two things we want to find here. Part A, we want to find S complement. So let's look at S complement first. In order to find the complement of a set, you have to know the universal set. So when we're looking at the complement for the set S, we have to go back up to the universal set and cross out any elements that are in S. And whatever's left is in the complement. So the elements that didn't get crossed out are 1, 3, 5, 8, 9, and 10. So S complement is the set containing the elements 1, 3, 5, 8, 9, and 10. Now let's move to T complement. First of all, I noticed that T was written in set builder notation. So the first thing I would do is write out T explicitly before even thinking about forming the complement. So we need to know what those elements are explicitly. So we're looking for the numbers less than 10 that are inside the universal set. That would be the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. But we also want those to be counting numbers that are odd. In other words, the numbers that are less than 10 and odd. If you look at the numbers that I have put in the rectangle indicating that they are less than 10, the odd ones are 1, 3, 5, 7, and 9. So written out explicitly, T is simply the set containing the elements 1, 3, 5, 7, and 9. Now you've done all this work, but we only found T. We want to find T complement, so don't forget, you've only found T now. We wrote out T explicitly. T complement is found by going back to the universal set and crossing out every element of T. If you do that, you cross out 1, 3, 5, 7, and 9. You're left with 2, 4, 6, 8, and 10. So T complement is the set containing the elements 2, 4, 6, 8, and 10. Just need to practice. There are two fundamental results concerning the universal set and the empty set. First of all, because the universal set contains all elements under consideration, the complement of the universal set then has to be the empty set. The complement of everything would be nothing. Secondly, the complement of the empty set is a universal set because the empty set has no elements and the universal set contains all the elements. So the complement of nothing is everything. The complement of everything is nothing. The complement of nothing is everything. If we want to do this symbolically, I could write U complement is equal to the empty set. And remember, there are two common symbols for empty set: the circle with the slash through it and the braces with nothing in it. So if I'm looking back at that first result, the complement of the universal set is U complement. It's equal to the empty set. Now, you don't have to write both of those symbols. I'm just writing them both for completeness because you see them both occasionally. You need to know that if you see either one, it means the empty set. The complement of the universal set is the empty set. That's the symbolic way of writing it. And the complement of the empty set, whichever way you write it, either the open circle with a slash through it or the braces with nothing in it, the complement of the empty set is the universal set. And remember that I don't have to write both of those symbols for the empty set. I just write one or the other. I'm writing both for completeness here. Let's talk a little bit about the concept of subsets. Consider the set of letters in the alphabet and the set of vowels, the set containing A, E, I, O, and U. Every element of the set of vowels is an element of the set of letters in the alphabet. Having said that, the set of vowels is called a subset of the set of letters of the alphabet. We'll often find it useful to examine subsets of a given set, so this is an important concept. Formally, a set A is a subset of set B, denoted by, and you see the symbol, it's the set A, and then the symbol is a sort of a sideways U opening to the right with a bar under it. A is a subset of B, if and only if every element of A is also an element of B. Just like I was talking about, the set of vowels is a subset of the set of letters of the alphabet because every vowel is also a letter. Here are two fundamental subset relationships that I want to emphasize. A is a subset of A. In other words, a set is a subset of itself by definition. And the empty set is a subset of A, and this is true for any set A. A set is a subset of itself, and the empty set is a subset of every set. So every set automatically has a subset equal to itself and the empty set. As we've done with other symbols in this course and in previous courses, if you put a slash through a symbol, it typically means not. A is not a subset of B, and look at the symbol. It's the subset symbol with a slash through it. It means that A is not a subset of B. To show that A is not a subset of B, we must find an element of A that's not an element of B. So if you want to show something is not a subset of something else, you have to find an element in that set that's not in the set that you're claiming it's not a subset of. Let's look at this and do some true-false. If I ask you, is this true or false? A set containing 5, 10, 15, and 20 is a subset of the set containing 0, 5, 10, 15, 20, 25, 30. All you have to do is start on the left and element by element look for that same element on the right. So you notice that the 5 inside the left set is in the right set, 10 from the left set is in the right set, 15 from the left set is in the right set, and 20 from the left set is in the right set. That's what you need to show that something's a subset of another set. So that statement is definitely true. How about this? W is a subset of N. Remember, W, the capital W, is the symbol for whole numbers. The whole numbers are the counting numbers with 0 thrown in. So it's the set containing 0, 1, 2, 3, 4, on in that pattern. The natural numbers is the letter N. The natural numbers are the counting numbers. They start with 1. 1, 2, 3, 4, ... which means it continues in that pattern. So you have to look at each element on the left and see if you can find a match on the right. And the very first thing you look at, which is a 0 on the left, does not have a match on the right. That means the statement is false. The whole numbers are not a subset of the natural numbers. How about this? the set containing 2, 4, 6 is a subset of the set containing 2, 4, 6. Now remember, we just talked about this. Every set is a subset of itself. And if you see, by doing the same thing we did for the others, there's a 2 on the left, it appears on the right. There's a 4 on the left, it appears on the right. There's a 6 on the left, it appears on the right. Therefore, it is true. But anytime you see a set compared to itself, a set is always, by definition, a subset of itself. How about this? The empty set is a subset of the set containing 1, 2, and 3. Now, if you remember what I said just a few minutes ago, you'll have this immediately, and that was the empty set is a subset of every set. So it doesn't really matter what's on the right. If you've got the empty set with the subset symbol, whatever you put on the right, it's going to be a true statement because the empty set is a subset of every set. That statement, therefore, is true. The English logician John Venn, who lived from 1834 to 1923, developed diagrams which we now call Venn diagrams that can be used to illustrate sets and relationships between sets, and I find them extremely useful, and I think you will too. In a Venn diagram, the universal set is represented by a rectangular region, and the subsets of the universal set are represented by oval or circular regions inside of the rectangle. This Venn diagram in particular shows a universal set U and one of its subsets A. The region outside of the circle but inside of the rectangle is the complement of the set A. So A is the set represented by the circle itself. A complement is represented by the area outside of the circle. Let's list every subset of this set. Say we have a capital C set, which maybe C stands for condiments, and the elements are mustard, ketchup, onions, and relish. Starting off with the empty set, because we've already discussed that the empty set is a subset of every set. That's the only subset that doesn't have any elements. Now let's move up to the one element subsets. We just take each condiment one at a time and put it in a set. So you start off with mustard, you do ketchup, you do onions, you do relish. That's all the possible subsets with just one element. Now let's move to the two element subsets. Have to have some organized pattern here, so I'm going to start with mustard and match it with every other condiment. So I'll say mustard ketchup, then I'll say mustard onions, then I'll say mustard relish. I've matched mustard with every condiment. Now I'll move over and do the same with ketchup. I've already matched ketchup with mustard, so now I'll move to ketchup with onions and then ketchup with relish. Now I've matched ketchup with every condiment, so I now move to onions. Well, the only condiment I haven't matched onions with is relish, so I match onions with relish. Now let's move to the three element subsets. The easiest way to think about this, there are only 4 elements in the whole set, so you'll get a 3 element subset by eliminating a condiment each time. So if I eliminate relish, I get mustard, ketchup, onions. If I eliminate onions, I get mustard, ketchup, relish. If I eliminate ketchup, I get mustard, onions, and relish. And if I eliminate mustard, I get ketchup, onions, and relish. And I claim that the only remaining subset is the 4 element subset consisting of the set itself. In other words, all of them. So how many subsets does that represent? If you count them, you'll find out that a 4 element set has 16 subsets. If I change it to proper subsets, remember the only difference is whether the set itself is a subset. So if I'm doing proper subsets, I have to leave out the set itself, so the 16 drops down to 15. So if I'm counting proper subsets, there are only 15. It's always true that the number of proper subsets is 1 less than the number of subsets. Let's see if we can find a pattern here. We know that a set with no elements has only one subset, namely the empty set, and that a set with one element has 2 subsets, namely itself and the empty set. And although we haven't done it, it's easy to show that a set with 2 elements has 4 subsets, and a set with 3 elements has 8 subsets. We just discovered that a set with 4 elements has 16 subsets. Let's see if we can devise a pattern. If you look at this following information in table form, you can see that if a set has no elements, it has one subset. One element has two subsets. Two elements has four subsets. Three elements has 8 subsets. 4 elements, 16 subsets. I'm looking for a pattern here. Do you see one? Do you see something that might be a possible pattern? Notice that each one of those number of subsets is a power of 2. 1 is 2 to the 0, 2 is 2 to the 1, 4 is 2 to the second, 8 is 2 to the third, and 16 is 2 to the fourth. It seems as if the number of subsets is 2 to the power of n, where n is the number of elements. Although we've not proven that that pattern continues, it turns out that it does. So we have the following result. A set with n elements has 2 to the power of n subsets. Let's look at this example. Suppose a restaurant sells pizzas for which you can choose from 7 toppings. How many different variations of pizzas can the restaurant serve? Think about this. You could have a pizza made with no toppings. How yucky would that be? Or 1 topping, or 2 toppings, or 3 toppings, or 4 toppings, or 5 toppings, or you could say put all 7 toppings on there. Well, that just means we're looking at toppings as elements of a set, and we're looking at how many subsets of toppings can you have on your pizza. So there's an analogy there between subsets of a set and subsets of toppings to be put on the pizza. That means there are going to be 2 to the 7th, which is 128 variations of pizza from this restaurant if you count a no-topping pizza. So you could have a pizza with nothing on it. You could have pizzas with just 1 topping, pizzas with just 2 toppings, 3 toppings, and you can see that's just like counting subsets. So this idea of subsets can be very useful in counting problems. Relating this back to your calculator, you're going to be using the calculator a lot in this course, so you need to start learning how to use it. There's a button, which I call the power key. It has an X with an exponent of Y, and that's your power button. So if you wanted to find out what 2 to the 7th was in the most efficient way, you would enter 2 into your calculator, press the X to the Y key, type in 7, and then press equal, and that would give you 128. How about this? What is the minimum number of toppings the restaurant must provide if it wishes to be able to advertise that it offers over 1,000 variations of its pizzas? Well, first of all, we know that 7 toppings is not enough because 7 toppings only produce 128 different variations of pizza. So that's not big enough. So my suggestion is you just start off knowing that 7 is not enough and keep going up until you pass 1,000. So if you do 2 to the 8th, you'll find out that's 256. That's not enough. If you do 2 to the 9th, you'll find out that's 512. That's not enough. But when you get to 2 to the 10th, you finally passed 1,000 variations of pizza. Restaurant would have to have at least 10 toppings before it can legitimately advertise that it can provide over 1,000 variations of its pizzas.